good. Here we go. So 6 class periods left plus finals. Yes, we can do this. 6 class periods left plus finals. Homework today by noon. Most of you have turned it in. Don't forget to get that submitted by noon. I have a busy day today, so I probably won't get it back to you today, but hopefully tomorrow or by class on Wednesday for sure. So that's the first thing. Second thing, next homework assignment. I'm just pulling up Moodle here. I should have left it up and I did not. Next homework assignment, it is going to be from chapter 12, is due. Here we go. Wednesday, May 6th at noon. So Wednesday, May 6th at noon is your next homework assignment. We are going to do about half of 12.2 today, and then we will do the rest of 12.2 and 12.4 Wednesday, and then finishing out chapter 12 on Friday. We are skipping 12.3. So that's the next thing. Final exam, 2 weeks from today, during our regular exam time, 2 weeks from today, Monday, May, I think that's the 11th. Monday, May 11th at 8. Again, remember this is not, I keep saying final exam, it's just test. It's a test on chapters 8 and on. I think that's right. You're nodding at me, yes. Okay, chapters 8 and onward, and we will review the last Friday of the semester. Speaking of the last Friday of the semester, that is when your proof notebook is due. So, any questions on any of those deadlines? Trying very hard to over-communicate deadlines so you know when they all are. Anything for questions on any of those deadlines? I hear large equipment outside. I think my water is going to be off in a minute. Anything else before we get going? See if you guys can hear any of the banging either. All right then. So we talked about functions yesterday, last class period, and we said there were 3 different ways that we could define a function, right? So 3 ways to define a function. Just a quick review. 3 ways to define a function. First of all, by listing all the ordered pairs. And remember, that's what a function really is. It's a collection of ordered pairs, or another way to say it is a subset of A cross B, right? Subset of A cross B, because elements in A cross B look like ordered pairs. So a subset of A cross B. We could list all of them. We could do an arrow diagram, or we could define a rule. So those were our possibilities. Those are 3 different ways we could define a function. Remember that my notation for a function looks like f going from A to B, and then we will send little x to little y. I think I might have said little a to little b last time. Doesn't matter. Whatever letters you want to use are fine. Does not make a difference. Remember that A is the domain, B is the codomain, and the set of little f of x, so that x lives in A, that's the range. So remember that the codomain is the set of all possible outputs, right? And the range is all of the actual outputs, the ones that actually occur. Differences between codomain and range. Any questions on any of that review? Anything for questions before we go on to next section? Anybody, anything? Okay then, so moving on to section 12.2, I am going to, I don't want to say warn you, that's not really fair, but this is a section that you're going to, I also don't want to say struggle with, because that's not really fair either. Maybe the best way to say it is when I ask about this section in future classes, it's always a, oh yeah, we learned that. How did that work again? So this is a section that you're going to need to see a couple of times. You'll see it in this class. You'll definitely see it if you take linear algebra, or if you take abstract algebra, if you take some upper level classes, probability and statistics, it gets seen in all of those. So it's just something that kind of doesn't necessarily always stick on the first try. Maybe that's the best way to say it. That's okay, that's fine. You're gonna need to see it a couple times, so just keep that in mind and try to read through it a couple of times also. Injective and surjective functions. Injective and surjective functions. And again, it's not you and it's not me. It's most of the students that I teach, and it's most of the stories that I hear from colleagues at other institutions as well. It's just one that you need to see over and over, and that you need to have repeated a couple of times. Okay. I think the definition is kind of okay from the reading assignment, but there are issues in the reading assignment that I need to talk about also, and that reinforces that this is a section that you need to see a couple of times. It's fine. This is why we do reading assignments, because it tells me what I have to talk about. So let's do my definitions. We've got 3 of them. So we're going to let f be a function from a to b. So a is my domain, b is my codomain. Function from A to B. 3 things. First of all, f is injective. And there are 2 ways of saying injective. So I'm going to do both of them. If, here's the first one, for all x and y living in A, if x equals y, then f of x equals f of y. For all x and y living in A, if x equals y, then f of x equals f of y. You should be starting to think about the types of statements that we've done previously in this semester. This is in implication, right? It's an if-then statement. So it also is a universally quantified statement. We've got the for all. So you should be thinking about what you need to do to prove this and what you need to do to disprove this. That's kind of the thought process that you should take. Also, it's an implication. So that means we can also do the contrapositive, right? If it's an implication, the contrapositive is also going to be true. So we can say for all x and y living in A, the quantified part doesn't change with the contrapositive, just the hypothesis and conclusion. If f of x is not equal to f of y, then x is not equal to y. So you can use the regular statement or you can use the contrapositive. If f of x is not equal to f of y, then x is not equal to y. Either the regular statement or the contrapositive, either way. We're going to do a bunch of examples of this, but I want to get through the other definitions before we start doing some examples. Okay, so that's the first one. Secondly, f is surjective. F is surjective. If for all little b living in capital B, there exists some A living in capital A, so that f of little a equals little b. For all little b living in capital B, there exists some little a living in capital A, so that f of little a is equal to little b. So again, think about how you would prove this. We've got some quantified statements here. We have both a universal quantifier and an existential quantifier. So we can think about how we're going to prove this one. And then third, f is bijective. Bijective. If f is both injective and surjective. F is bijective if f is both injective and surjective. Okay, let's talk terminology first. So these are the fancy math words. These are absolutely correct. These are the fancy math words. These are probably not the words that mathematicians are actually going to use. Instead of inductive, we usually say one-to-one. Instead of inductive, we usually say one-to-one, and we don't usually write it out with words. Usually we just write 1-1. So usually we'll say one-to-one, and it gets written shorthand as 1-1. You're more than welcome to use that. Instead of surjective, we usually write onto. So we usually say F is one-to-one or F is onto. Those are usually the terminology that we use. For bijective, usually we will say one-to-one and onto. That's the way that it usually gets said, just kind of combining both of those. But you can also say one-to-one correspondence. So we can also say one-to-one correspondence. That's the other way that this can be said. One-to-one and onto, or a one-to-one correspondence. Okay. Also, let's talk about how to prove these things. So for this, we are proving an implication, right? We talked about the first one, injective, one-to-one being an implication. So we're needing to prove an implication. That means we get to assume the hypothesis is true. And my need to show is that the conclusion is true. Okay. So that's how we would do that one. We're proving an implication. So we get to assume the hypothesis is true, and I need to show the conclusion is true. So this is to prove. We should do that. To disprove, I need to find a specific example that makes the implication false. I need to find a specific example that makes the implication false, because this is a universally quantified statement, right? It was for all X and Y. So if you are disproving a universally quantified statement, you have to find a specific counterexample. And again, remember how we prove that an implication is false? This needs to be hypothesis true, conclusion false. This is why we talked so much about truth tables and that line in the truth table, hypothesis true, conclusion false. All right. We'll come back to how to prove surjective. I think that's going to be Wednesday as opposed to today. I want to do a bunch of examples on these so that you can get some practice in both proving and disproving. So let me stop sharing my screen for just a second and see if there are any questions at this point in time before we jump into some examples. Anybody, anything for questions right now before we jump into examples? No, we're good, we're happy? Okay, let's